we've already encountered some examples of dynamic equilibrium, but now we're going to formally discuss equilibrium and look at it in more detail. So a lot of the reactions that we've considered essentially go to completion. That is, all of the reactants get converted into products, except what might be left over based on limiting reagent considerations. An example of a reaction that goes essentially to completion is the combustion of octane, which is the equation that we see here. When this reaction happens, basically all of the reactants get converted into the products, and there aren't any reactants left over except for any of the limiting reagent. But that's not true for all reactions. Many reactions don't proceed to completion. Only some of the reactants get converted into products, and so we're left with a mixture of both reactants and products. And these reactions are said to reach dynamic equilibrium. And one of the examples that we've seen already is vapor pressure. So even when we're below the boiling point of water, some of the molecules are going to have enough energy to escape the intermolecular forces. And if those molecules happen to have enough energy to escape the intermolecular forces and also happen to be on the surface of the liquid, they can escape into the gas phase. But at the same time, the reverse reaction can happen. And if a molecule collides with the surface of the liquid, it can be reincorporated into the liquid. And so we have both processes happening at the same time. New molecules going from the liquid phase to the gas phase, and molecules that had already made it to the gas phase going back into the liquid phase. And at some point, or in the beginning of the reaction, right, it's mostly going in one direction. But at some point, the rate of the evaporation is going to be equal to the rate of condensation. And so while those processes continue to happen, the pressure above the liquid stops changing. And it's that point that we've reached equilibrium. The reaction effectively stops changing the concentrations of the reactants and the products, and we are at equilibrium. Now, as we saw in the last chapter, reaction rates depend on the concentration of the reacting species. And so when we start a chemical reaction with only reactants, the reaction can only go in one direction, right? We're only going to get the forward reaction. And so at the start, if I only have reactants, the rate of the forward reaction is relatively fast, and the rate of the reverse reaction is effectively zero. But as the reaction proceeds, we start to make more products. And once we have some products, the reverse reaction can now happen. And so as we make more products, the reverse reaction gets faster. And as we lose reactants, the forward reaction gets slower. Right? And dynamic equilibrium is achieved once these two become equal. Once the rate of the forward reaction is equal to the rate of the reverse reaction, we are at equilibrium. Right? That does not mean that the concentrations of the products and reactants are equal at equilibrium. It means they stop changing. And so in this example, at equilibrium, for this specific reaction, we have more products than reactants. And we can clearly see that the concentrations of the products and the concentrations of the reactants are not equal. But what happens at equilibrium is that the concentrations stop changing. And whether we have more reactants or more products is specific to the specific chemical reaction that we're studying. All right, so again, at equilibrium, the concentrations of the reactants and products aren't equal. They've just stopped changing. And so we want a way to quantify how much reactant or product we have at equilibrium. And we do that with what's called the equilibrium constant. And so we have to be careful about capitalization now, because we used lowercase k for rate constants. For equilibrium constants, we use a capital K. And the equilibrium constant is defined by taking the concentrations of the products and dividing those by the concentrations of the reactants. But the stoichiometry does come into play here. And so each of the concentrations of the reactants and products are raised to the power of their stoichiometric coefficients. So if the stoichiometric coefficient in front of the product C is this lowercase c, right, then we need to raise the concentration of C to that power. And the same thing for all of the reactants and products. Okay, so let's look at an example. Let's write the equilibrium constant expression for this reaction. So our equilibrium constant K is equal to the concentrations of the products. So I have carbon dioxide and water divided by the concentrations of the reactants. So I have the concentration of C2H6O times the concentration of O2. And then I also have to take into account the stoichiometric coefficients. And so the carbon dioxide needs to be squared, the water needs to be cubed. The stoichiometric coefficient for the C2H6O is 1, so we don't usually write the 1, it's understood. And then the oxygen needs to be cubed. All right, one other important feature of equilibrium constants that I haven't mentioned yet is they don't have units. If you go on to take analytical chemistry, we'll talk more about why that is. It may seem a little bit unusual, but the equilibrium constants do not have units. But as we'll talk about in a later slide, the units on the concentrations do matter. But the K itself does not have units. All right, so what does the magnitude of the equilibrium constant tell us? So we always compare K to 1, right? So if you notice, right, 1 comparing to 1 comparing to 1, right? When the equilibrium constant is significantly less than 1, right? So we're talking about K is less than 1, and so 10 to the minus 30, that's definitely a lot less than 1, right? That tells me that we have almost all reactants present at equilibrium. Very little of the reactants get converted into products when we have very small equilibrium constants. When we have a large K, so when K is much bigger than 1, that tells me that I have mostly products at equilibrium, right? Reaction with a very large K, and 10 to the 380 is huge, right? That's telling me that that reaction basically goes to completion. I have essentially all products present at equilibrium and almost no reactants. And then when K is around 1, that means I have significant amounts of both reactants and products. So a K of like 5 or 100 or 0.1, if K is bigger than 1, I have more products than reactants, but if these numbers aren't crazy small and crazy big, that means that this reaction truly is going to equilibrium, and I have some of both the products and reactants present at equilibrium. All right, to this point, when I've been talking about equilibrium and equilibrium constants, the way we've been measuring the amount of reactant or product is using concentrations. But that doesn't have to be the case. If we have a reaction in solution, then we're always going to use concentrations. But if we have gas phase reactions, we can use concentrations, we can use molarity, but we can also use partial pressures to represent the amount of gases. It works the same way, right? The equilibrium constant for this reaction, whether I use concentrations or pressures, it's still products over reactants. I still take into account the stoichiometric coefficients. The only difference is, in this case, I'm using molarities. In this case, I'm using partial pressures. And we need to be careful. We should be using atmospheres. Now, the magnitude of the equilibrium constants, or the exact numbers, can be slightly different whether I'm using concentrations or pressures. And so we have to be careful. Sometimes we'll use Kc when I'm saying specifically that I'm using concentrations, or if we're using pressures, we might call it a Kp. Okay, another thing that we need to consider when dealing with equilibrium constants is that only gases and aqueous substances appear in our equilibrium constant expressions. Pure liquids and pure solids do not appear in the equilibrium constant expression, and instead they just have a value of 1. And so if in this example, for this reaction where I'm converting calcium carbonate into calcium oxide and carbon dioxide, the amount of carbon dioxide doesn't depend on the piles of the calcium carbonate and the calcium oxide that are present. As long as we have some of each one, the equilibrium doesn't depend on them. In this case, it would only depend on the gas, because solids would not appear in our equilibrium constant expression. All right, and so just to finish up that example, if I was going to write the equilibrium constant expression for the same reaction that we just saw, it would be K is equal to the concentration of the products. So calcium oxide is a solid, so that would get a 1. CO2 is a gas, so here I could use, whether I'm doing KCs or KPs, I'm going to write a KC, so I'm going to use the concentration of CO2. And then for the reactants, the CaCO3 is our only reactant. It's a solid, so it doesn't appear in the equilibrium constant expression. Instead, it just gets a 1. And so then effectively, the equilibrium constant expression for that reaction is just the concentration of CO2. All right, and so the next video, I've got some example problems that we can do with what we've so far learned about equilibrium and equilibrium constants.